We've talked about fluids, and we've talked about a number of different aspects of them. Let's see if this will run.
Perform the following 6.
And so one aspect of fluids that we talked about is Newtonian fluids and also thixotropic fluids. Drilling muds are thixotropic, we made the point before. And that is that when they're static and you try and shear them, you have to apply a finite shear stress to get a velocity. In other words, they're like solid. You have to apply a certain mixing to them before you get any motion at all. But once you do mix them, then they behave like liquids again. And so drilling fluids, drilling muds, are to be able to, that when you drill a hole in the ground and the pressures on the sides of that well are essentially reduced because you don't have the rock forcing it open again, the drilling mud is to provide two facilities. One is it pushes back on that well bore with some weight, and by adding mud to the fluid, barite or just bentonite, barite is a relatively dense mineral, you can actually apply a larger force to the wall than it would be if it was just water. And so using a balance of drilling mud to be able to counter the pressures that are present within the formation, especially the fluid pressures that are present within the formation, allows you to keep the hole open and to be able to keep on drilling at depth. And I guess also it serves the purpose of the fact that it's pumped down to the bottom in the center of the drill pipe, which is drilling, and it comes around the outside of that drill pipe on the inside of the well bore, is it actually removes cuttings and takes them up to the surface as well. So it provides multiple facilities, I guess, in that regard. And so in calculating, those are the mechanisms by which drilling fluids work. In calculating the magnitudes of the fluid pressures that you get at every depth, then you can use the kinds of methods that we've talked about already in this class. And so we now know how to do that if it's a liquid. And we now know that if it's a liquid and of constant density, then indeed it is a straight line as we go down here. So that's one concrete example, no pun intended, concrete example of what we're interested in. Another one, maybe related to Hurricane Harvey, Tropical Storm Harvey, is related to the safety of dams. Some of the dams in around Houston have started failing, not in the same way as this, but have been overtopped and have eroded. You might remember last year in February, Oroville Dam in California, with a big snowfall and big snowpack and early melting in February, I think it was, started coming up to its level, and the emergency spillway was activated, which is just a route that's around the dam that is slightly lower than the crest of the dam that allows water to bypass, and it was being ripped out by the very, very large flows that occurred. And if that erodes back into the dam, then it collapses. Another form of failure, which thankfully we don't see very often these days because now we know about them, from 1959. The first of these was the Malpasse Dam in the south of France near the French Riviera. It's an arch dam. Actually, there was a pretty decent video, I thought, here. Let me do this. It was an arch dam in the south of France. And arch dam is built across a valley to dam a river. It was constructed in the early 50s. It's very thin, and it relies on the fact that on the abutments, the forces are applied on the abutments with this curved arch pointing upstream. And so it pushes on the abutments. If you imagine trying to brace yourself against something, the water's behind my back, and the arches of the dam are pressing against it. So the fluid is on the upstream. And so one consequence of what we're talking about here is we're talking about fluid pressures at a point, but we knew from that drilling video that the pressures are continuous as you go down. So if we wanted to calculate the forces that are applied on that abutment, we could integrate that pressure distribution, and we'd know what the forces are that are applied. And in this case, unfortunately, the barrage is French for dam, ruptured, which is what that's saying. And instead of being this beautiful arch that goes across the river with an impoundment upstream of it, it broke. It broke because the abutments moved, because there are faults in there, and it failed as a result of that. And I don't know how many people died, but certainly a number of people did die in that particular deal. And I think another consequence of this is people who do things like dam break analysis to be able to see exactly what happens if you suddenly release a wall of water coming down a valley around the remainder of the stream bed that used to be there. And typically people locate in stream beds because there's water supply historically. And so if you dam upstream of that and there's a collapse, then that's often a problem, as it was in this particular case. And so this kind of embodies some of the things we have in this class. We're talking about fluid pressures only at a point. If we want to know what the forces are on a structure, we can integrate those fluid pressures to be able to calculate what forces those apply, and we could calculate whether it fails or not. And that's really what we'll move on to in week 3, is talking about fluid pressures applied on surfaces and what those might be. Exactly the same way that, well, not for fluid statics, but for fluid dynamics, the pressures on the wing of a plane are due to the motion of fluids, and that's what gives lift. But the pressures on the cabin of the plane would be an example of fluid statics at work, hoping that the fluid pressures on the inside, where it's a pressurized cabin, aren't large enough to be able to rupture the skin when you're flying at 36,000 feet. Okay, so that's kind of where we're going with this, and I will leave that. So it might seem a little esoteric what we've talked about so far. I guess I want to do that, and to see exactly where this fits in, but that's basically trying to make the case of exactly where we're going with this. So let's get rolling with this. So So we've said this a number of times. Perhaps it's worth saying multiple times. I mean, these are the things that we've talked about so far. We know that pressures at a point are the same in all directions. We know that when we have zero accelerations in a system, then the system of equations that we have, and I'll just sit back to these ones because we looked at them yesterday. The system of equations that we have, and if we write out, for instance, the ones that are represented by the pressures in the z direction, are something like, not something like, change in pressure with depth minus unit weight of the fluid, and this term minus density times some acceleration in the z direction equals 0. We know that this term is the unit weight, as we call it, gamma. Not a very good gamma there. And even though we've started talking about, in some of those things that we looked at, the kayaking videos, falling off a waterfall, you could ask yourself, for instance, what are the pressures that you feel as the water feels as you're falling down through space? Well, it's exactly the same as what the kayaker would feel as you're falling down through space. It's weightless. It's like the vomit comet, NASA's vomit comet. Goes up and then does a parabola, and as it goes across the top of the parabola, all of a sudden you're weightless for a few seconds, and you're floating around in the cabin. Well, the reason for that is that in this particular case, when you're falling, if you think of if any of you has a water bottle here, and I took your water bottle, can I? And I drop it, this is exactly what we're talking about. This is the square differential volume that we have in a container. When we talked about the pressures in a column, we took one of these and we took one below it and we took one below it, and we said that this is linear because the weight that's actually on the bottom of this is this. In the same way, we can apply an acceleration to this, and so the acceleration to this is if you're falling downwards, what is that acceleration? And so if we're falling down with gravity, which direction is that acceleration? Downwards. And so for our coordinate system, where we've taken x as horizontal but z as positive upwards, this is minus g. This is minus g, this is plus g, and so this then becomes a positive. These two cancel out and become 0. And so the pressure distribution as you go down, if you thought about that waterfall as a continuous stream of water, the fluid pressure in there is 0 because it's falling through space. And so the equations that we have allow us to be able to calculate that. But anyway, so that's just maybe an aside that we can calculate some things, and we will talk about accelerating fluids principally in 4.1, so the beginning of week 4, before we start talking about fluid dynamics. And of course, the Bernoulli equation, we can actually derive directly from that expression we just looked at. So that's kind of an aside, but let's get back to today to see exactly where we are. The other things that we know are that if there's no accelerations, then the pressure changes absolutely conform to this rule. We know that if it's an incompressible fluid, then taking this and integrating it gives this, which we used. If it's a compressible fluid, then we have to account for the fact that density changes with fluid pressure. And so we can accommodate that as well, and we've done that. The other thing that we know from this is that if we go horizontally, this is just a fancy way of saying that if you go horizontally, pressures don't change. And we've used that, and we'll use that today. So really what I wanted to do today was just go through some examples that kind of hopefully clarify and exhibit the traits of manometry that we kind of introduced yesterday, on Wednesday rather. And to do that, we'll use the manometer rules. So all of the things that we did in the first part of the week on Monday, which are really up to this point here, were expressed in something that we talked about on Wednesday. And these are the manometer rules. And there are only 5 of them maybe. So if you go up in a fluid, you subtract pressures. If you go down in a fluid, you add pressures. You know that from going down in a swimming pool. Those make sense. So this is just my shorthand for that. If you go horizontally in a fluid, then the pressures are the same at that same elevation. If it's evacuated, then it exists at the pressure of the vapor pressure. We did the barometer example last time. And if it's in a gas, as we go up and down, typically compared to the densities of the fluids, it's probably 1,000 times less than the density of the fluid. The difference is so great and it's so trivial that we can neglect it. So these are the 5 manometer rules, if you like. 1, 2, 3, 4, and 5. And so that's what we need to be able to do the things that we'll do today. Okay. So let's talk about. So the examples that we go through are the ones that are listed there. And let's just work through them. So can you see that? Do I need to make it larger? I'm not sure how big it is. I guess I want to be able to use the palette just to change colors because I like doing that. So here's an example of a bucket upside down that has a pipe coming out of it and a manometer fluid. This is some kind of gauge fluid. In this particular case, the gauge fluid is 2.5 times the density of water. So specific gravity, we really haven't talked about, but it's equal to the density of the fluid divided by the density of water, by definition. So it would be 2,500 kilograms per cubic meter. I'm not sure what that fluid is, but it's, and actually this one is in English units. Again, I'll repeat, none of your exams will be, your exams will only be in SI units. And so what's happened is that this bucket's been put in the fluid. Originally the bucket would have been in the fluid and the water level would have been here. It has the manometer is then filled up and then the bucket is pulled up. And if the bucket's pulled up, then by suction, it's pulled up the fluid, which is here, to fill a portion of the bucket. And what is the question? I guess the question is, what is this value of height that is present within this system? And so we do it in exactly the same way that we've done other ones. We'll work from something that we know to something that we don't know. And so we have to figure out exactly what we know in this case. We know that the pressure here is atmospheric. And so if we use gauge pressure, as 0, then this is by definition 0. This is atmospheric pressure as well. This is the top of the fluid. This is 0. We know that we can get from this point to this point in the same fluid, and so this is also 0. So those are our kind of boundary conditions that we know. And so the rest then is to be able to link the magnitude of the fluid pressure at this point to the fluid pressure at this point, because if we do that, probably this value of head is going, or height, is going to be included in that equation. And so we just use those manometry equations. So this one is using the pressure, this is using dP dx equals 0, right? This is in the x direction. So let's do it. I'm not sure I'll do the number calculations, but let's do the actual physical calculations. We know the pressure here. It's usually best to start where you know a pressure and work to somewhere where you don't. But actually in this case we know the pressure here and we know the pressure here. So it really doesn't matter which way we do it. So let's start here. So we start with pressure B. And we're going to go to this point here. We're going up in a fluid. We subtract minus 2 feet times the unit weight of water. I'm guessing this is water, right? So that gets us to this point here. We know that this is air, and so the density of this is trivial compared to the fluid. So the pressure at this point here is exactly the same as this point here. So another PA is equal to PA prime. So we find ourselves here. And so we can go here by adding nothing, I guess. I won't add a 0 here. And so now we're here. This is gauge fluid. So we can go from this point to this point, and this is still the same pressure as PA. Nothing's changed. And we can add this pressure here, or subtract, I guess. And this is going to be equal to this H minus 3, right? All feet, both are feet, multiplied by the unit weight of the gauge fluid. And that's equal to PB. So we know that these are both 0. We know that this here is going to give us something like the unit weight of the gauge fluid is equal to 2.5 times the unit weight of water because of this, because this is equal to 2.5. And so this is going to be equal to 2.5 times gamma W. And we have an expression which is equal to, what do we want to keep? So we have minus 2 times unit weight of fluid plus 3 times 2.5 times the unit weight of water, which is this term here. And I'm going to add on the other side, is equal to H times gamma W. And if I just divide both sides through by 2.5 gamma W, we have an answer, right? So we have the height is equal to some magnitude, and you can work it out from this. So what you see is, do I believe that in this particular case? What's the answer that they get here? So it's 3 times 2.5. So I think that H should be less than 3 feet. Is it less than 3 feet? because it's got a 2.5 here, right? So yeah. So anyway, so the value for H is going to come out to be, it should actually be down here. So I don't know what that comes out to, because this is suction, right? And so this is suction means that the pressure at this point is actually less than atmospheric, and so only if it's more than atmospheric would it actually be that it's taller, because you have to add pressure to go up here. And so whatever this magnitude comes out to, I'm not going to do, I hope that I've done the calculation right. Maybe, is it 2.2? Okay, good. Well, I know it's 2.2, but is my calculation 2.2?
Yeah.
Okay, good. I'm amazed myself. Thank you. So that's it. So you just have to it's actually a recipe for doing it. And I guess the other question is, what's the magnitude of the force that you have to apply to this to be able to pick this up? And so you can do that in two ways. You can probably work out what those are. One is you could do a free body diagram to say that if you're pulling up on this plate with some force R, it is equal to the pressure that's applied on the underside of this. And this is the pressure A. And so the force would be PA times the area equals, it's going to be the reaction of R. So you could do that.
Wouldn't there also be the atmospheric pressure pushed down? Or?
No, we've done it in gauge pressure. So it's already included, yeah. So sometimes it's useful to do gauge pressure. Yeah.
Why is it that you can replace the specific gravity of air or the specific gravity of gas with water?
Specific gravity. Oh, so this is not G. This is gauge fluid. Okay. So this is a liquid that's in here. So yeah. So it's too denser than water. So yeah. This is not gas. This is the gauge fluid in the manometer. So this is one way to do it. Any thoughts of another way to do it? From what we did with capillaries and height rises in capillaries? The other way to do it is, we know that the pressure here is atmospheric. We know the pressure here is atmospheric. We could just cut this thing off at the knees and look at the amount of water in here. And so in other words, if you think about this volume of water here, it will have a weight that is acting downwards due to this whole thing here, and you could work out exactly what that is. It's area times 2 feet, which is a volume, multiplied by unit weight of water. And that has to equal R also. Because we can just isolate this as a free body. We're pulling it up physically. We're pulling it up by the bootstraps, if you like, or by the braces, suspenders, I guess you call it in this country. And that would be the same. So you can do that calculation. This calculation here and this calculation here should give you exactly the same results, because it's physically the same system, right? So I think the challenge in this class is to think about how you do these things. It's not really an equation-driven class. You can't just, what equation do I use? You have to actually put things together. So I think that is the challenge in terms of thinking about things in this class, right? This is kind of more complicated than we need. Let's just do it very, very. It's never going to be quick. So this is called a differential manometer, and the idea is that you have something with you want to measure the difference between these two pressures, P1 minus P2, and you want to measure it very accurately. Many times in experiments you don't want to measure the absolute pressures. It's not so easy to measure an absolute pressure with a pressure transducer and a different absolute pressure with another pressure transducer and subtract the results, because there's inaccuracies in those pressure transducers. They're only valid over a certain range of pressures. So sometimes it's easier just to measure the difference in pressures between them. And, well, actually I'm not going to go through this other than to make the case that it has a gauge fluid in here, which is a different unit weight from the gauge fluid that sits on the top, and you're measuring the pressure in a gas. And really the basic idea is that in looking at a pressure differential, what would happen if pressure 1 is not the same as pressure 2, then this thing would start out at the location where the gauge fluid is uniformly across this at this elevation, and the pressures or the fluid levels within the system are where the blue lines are. So that's how it starts out. If you then change the pressure in P1 to some different number, in this case I guess you'd be increasing the pressure because it drives this down, then what would happen is that the elevations change so that instead of being the blue line, it goes to the green line, and instead of being the blue line here, it goes to the green line, and it changes by some height delta H. And the implications of that are that the blue line that started off here now goes to the green line here, which is down, and the green line here. And so the idea is that it would actually work just fine if it was just a single fluid and that you could identify the location of this interface. The only reason that you need to use two fluids, two immiscible fluids, two fluids that don't mix, is that you can track this boundary. And basically the idea is that this small fluid pressure will result in a small change in elevations of these two, which are defined by the magnitude of this pressure change. So actually this pressure change, delta P, which is equal to P2 minus P1, defines this height, as we've seen. But this might be, in a light fluid, a small amount. If you have a gauge fluid which has a marker and it's in a very small tube, the volume change that you get in this has to be exactly the same volume change that is experienced in this and in this. And so the fact that this moves a much larger amount, it amplifies the effect, and therefore you can pick it up. So I'm not going to go through the derivation for that because it's more involved than we need to in this class, and you won't see that in an exam. But it's a bit like what we talked about at the end of class last time, and that is this idea of an inclined manometer, is that we know that the elevation changes between a pressure in this pipe and a pressure in this pipe cause a change in the gauge fluid by some small amount. If this change in the gauge fluid is not very large, then one way to be able to magnify it is to look at its influence or its expression, if you like, on an inclined tube. An inclined tube, if you measure it in this direction rather than this direction, will just amplify it depending on the inclination of the tube. And so this differential manometer that we've talked about in just descriptive terms is basically doing that. It's amplifying the magnitude of the signal because this change in elevation of these two fluids relative to each other is going to be much larger than measuring the change in elevation of the two fluids that you measure here. Nothing more than that. And so you can go through that, or you can look at the previous year's notes where we actually did do this in full, I guess, last year. So if you're interested, then do that. Okay? All right, let's do another one. We said we're just doing examples. So here's another one. Let's read the question to see what's being asked for in this particular case. So I guess I want to get both of them on the same page at the same time. So what do we got here? So when you see these aren't little spheres. These represent pipelines disappearing into the page. And so this is a way of measuring pressures between different pipes going into the page. So there is a pressure PA in the center of this pipe. There's a different pipe here also going into the page. And these are two different fluids. Two pipelines. Again, it's in English units. There's fuel oil with a specific weight of 53 pounds per cubic feet. Water is what, 64 something? So it's less dense than water. So this has unit weight A, which is this, and it fills a portion of the manometer, but stops here. There's a second one flowing in the other pipe, which is slightly denser, and this is unit weight B. And they're separated by a gauge fluid, which is unit weight, let's call it Hg, not for gas, but for the gauge fluid, which is the same as the unit weight of mercury, H sub G. And we've got an air bubble. And so half the battle in all of this is figuring out exactly what the question's asking you. It's asking the pressure in B if we know the pressure in A. So we know that this is equal to 15.3 psi, which isn't important, but what's important is we know this. And so what we want to know is the magnitude of B. And so we would like to be able to write a simple equation that gets us from A to B. So let's do that. So we can write pressure A. So we start here, if you can see this point. And we start moving from here down the tube. We know that we can get to this point before we change fluid pressures. And so we can go to this, which is 3 inches plus 18 inches. And it's in the same unit weight fluid. We're going down. So I guess it's like going in a swimming pool, going from here to here. Our ears are going to be hurting. So we're adding fluid pressures. So 3 inches plus 18 inches. Multiplied through by the unit weight of A. Unit weight is defined in feet, so I guess we should, to be consistent, we should probably divide through by 12, which gives us fractions of a foot, right? So we've gone down, we have a high pressure. So we know that now we can go to this point here, and that should be exactly the same as this point here. So again, we go down, plus 6 over 12, so this is inches in a foot, multiplied by gamma gauge fluid. That gets us to this point. We know that from this point, can you see that on there, by the way? Yeah, you can. That gets us here. And now we go up. We're going up, so we go up 6 plus 18. I won't make that 24, but I'll just write it up. Multiplied by the unit weight of B. That gets us to this point here. And then we know that this is a gas and it's also the same fluid. So we can go to this point here. These have to be at the same elevations. And so we're at this point here, which is where we are. And we have to add 2 inches of depth, right? We're going down, so it's 5 inches minus 3 over 12 times the unit weight B. And I've run out of space. But this is equal to PB. And so this is the thing that we want. And we're actually arranged in the right terms to do that. We know that this is equal to 15.3 psi. Have to make sure our units are in the right things. We know this. We know this. We know this. And we know this. We have everything we need to do that. And so it's just a recipe to be able to work across there. And I think that's basically the, hopefully this is exactly the way, yeah, you see all those terms here. So this is here. This is here. Looks like I even got my signs right. and this is 2 over 12. Right? That's it. So you just have to, so the key things to know, I guess, are start off your equation where you know something, which is this, and then work through to where you don't know something. And remember that when you go down the fluid, you add. When you go across a fluid, you have to be at the same elevation, and you have to be able to get there from the same, in the same fluid. Then the fluid pressures have to be the same here as well. And when you go in a gas, the densities, well, you could do, actually you could go up, and then you could go down here, and it wouldn't make any difference. In this case, it doesn't matter about the density. And then you end up at this point, okay? So, anyway, so you can see that at your leisure. So, maybe a more challenge. So again, the crux, I think, of all of these is being able to figure out exactly what you're being asked and what you know, and be a little bit creative about how you put these things together. So here's a question on a concrete form. A concrete form for a step, which is open at the top so you can pour the concrete in, and then is closed. And where the form is filled up all the way with concrete, and it has an open base, sits on the ground. And the basic question is, what weight of material do you have to put here to stop this thing floating off and spilling all the stuff from underneath it? What's the minimum weight that you have to put on this to be able to do that? And so there's a couple of different ways you can do this. The one that's done here, let's go through it because it's done here, is you make a free body diagram. And that free body diagram, you merely cut it at the base, where it's open, and you look at the balance of the forces as you cut around this whole thing. So you'd cut around this whole thing on the outside here. We've talked about free body diagrams, I'm sure, in your physics class. Physics 211, I guess, should be the prerequisite for this class rather than 212, right? And this is here. So if you isolate this with a free body diagram, here are the forces that are acting. You have the weight of concrete that you're going to fill this thing up with, which is this black stuff here. You have the weight of the form, which is the wooden form that you have, which is also pulling down. And you have a weight of a bag of sand that you put on this as well. And pushing up against this is the fluid pressure that you have that's acting on here. That's the reaction. You know that if you looked at, for instance, the fluid pressure on the side here, and you drew this, you know that the fluid pressure would look like this. And so this magnitude here is equal to gamma concrete times this height, right? This is pressure. What's that? And it is, they are 8-inch steps, so this is 24 inches, which is 8 plus 8 plus 8, right? 1 step 8, 1 step 8, 1 step 8. And so this pressure that's acting here has to be exactly this magnitude. So PB, this is PB, pressure at the base. And so PB is equal to the unit weight of concrete multiplied by the height. This height is 24 inches. And so the rest is just a calculation in terms of volumes. That's the one important step in this, is to realize that you're not going to divide this up into a step and the pressure on this base is equal to this height, because that's not the way it works. The pressure at this base, we know that the pressure at this base is equal to this height here. And so the net impact of this is that also acting on this tread, there's a fluid pressure acting up, and that fluid pressure would be equal to what? P step is going to be equal to H step times unit weight of concrete, right? But this is irrelevant. It's irrelevant because we've drawn our free body on the outside of the form. This is acting on the inside. We don't care about this. So we don't care about that at all. But the point is that the pressure acting on the base of this is uniform all the way over, and it's given by this magnitude. So the rest is just a calculation to figure out what the volumes are. So the weight of concrete, if I go down, I won't write them out, but you can see exactly the calculations are done here. The weight of concrete is the unit weight of concrete times the volume of concrete. The volume of concrete is, each of these treads is 10 inches. This is the tread, right? And so the volume of concrete here is 10 inches by 24 inches. This is this first component here. The second component is this one here, which is going to be 10-inch tread times 8 inches plus 8 inches. And the third one is going to be this, which is 10-inch tread times 8 inches. Multiplied by the width of the step into the page, which is 3 feet across, and multiplied by the unit weight. So the bottom line is we have a magnitude of the weight of concrete. I've covered these up, but the weight of concrete is one of them. The weight of the form you're given is 85 pounds. I don't know if you can see that here, a bit small, probably on the screen, but that is this. The most important one, is that me, is the pressure that's acting on the base. The pressure acting on the base is the unit weight of concrete times the height, and it's multiplied through by the width into the page. So the pressure acting is the unit weight of concrete here, gamma C. The depth, which is 24 inches over 12 inches per feet, which is 2 feet, which we've called H, is the pressure. And if we multiply the pressure, which is this magnitude here, by the area is 30 feet into the page, 30 inches across here. So this is 10 inches plus 10 inches plus 10 inches, right? Which is the length across here. And so this is the 3 treads added together, the depth of the step into the page, which is the area. And if you multiply these two together, you get the pressure at A times the area. And so, unfortunately, I've kind of covered this up, but you see the free body diagram is that you have these 3 effects. You have the weight of the concrete acting down, which you have given right here. You have the weight of the form acting down, which you have right here. You have the weight of the sand, which you don't know, which is this one here. You know this, weight of concrete, weight of the form, and you have the pressure acting on the bottom, acting in the opposite direction, hence the minus sign. And if you sum those up, you end up with a magnitude that you calculate here. And so that's one way to do it. Yeah.
I think you might have touched on it, but would you also be able to just take, like, ignoring the concrete, take the pressure at the top of 3 and the top 2, and use the weight of the form?
You the man. Yes. So the other way to do it, so we've done it by drawing our free body diagram that does this dotted line that goes around here. There's an alternate free body diagram that we could use. I guess I could do this. Watch this. Which does... I thought that got rid of stuff. Apparently not. Well, I can do this, I guess. Fantastic. So the other free body diagram you could use, great question by the way, is to do this. And so the other free body diagram you could do is one that, again, goes on the top of the form like this, but then goes through the form like this. And it completely ignores the weight of the concrete. Now, the reason I didn't get rid of this is because we know that this pressure here would be the pressure, so the pressure on step 1 would be this magnitude, which is 0. The pressure on step 2 is this magnitude, which is acting up here. And the pressure on step 3 would be this magnitude here. And that would be acting here. So you could also do this by putting the weight of sand plus the weight of the form minus P1A1 minus P2A2 minus P3A3 equals 0. We know that all of these A's, A1 equals A2 equals A3, and they're all equal to 10 inches, which is the size of the step, times 3 feet. Right? So this length multiplied by 3 feet into the page. And we know, for instance, that P2 would be equal what? It's equal to 8 inches times the unit weight of concrete. In other words, this height here, which is 8 inches, times the unit height of concrete. And I guess we also know that P3 is equal to 8 inches plus 8 inches times the unit weight of concrete. Yeah, so you can do it. Great question. So, as I like to say, there's more than one way to skin a cat. So don't report me to PETA. But anyway, so that's it for today.